I need statistics, buddy. If you weren't a child in the 80s, you're not going to get these references. Don't even try, okay? Let's do what's called conditional probabilities. Let me warn you, this is one of the top 5 hardest things in the entire class. So if you don't get it right off, it's okay. Lots of people feel that way, but I'm going to show you a couple different methods. I'm going to do a couple videos and keep at it until you get this, okay? Let's start with what happens if you go in for breast cancer screening. So if you have breast cancer, there's a 92% chance that it'll catch it, and that's good. If you don't have breast cancer, there's a 97.7% chance it won't catch it, and that's good. Now, these numbers do depend on which type of woman we're talking about, and we are talking about a woman who has a real chance of having cancer. So only 0.0147%, these would be older women who have a high risk. Now, those percentages look high, which is impressive, but here's the question I want to ask, and the answer is going to surprise you. If a test detects cancer, what's the probability that you actually have cancer? And you're going to say, well, you have cancer because the test says you do. No. Sometimes you can come in without cancer, and the test, it's a small chance, but the test will actually come up saying that you do have cancer. So you can't just claim that if the test is positive, you're guaranteed to have cancer. We call those false positives. And it's very stressful for the woman to hear, I need you to come back in. And they're thinking, what's the chance that I do have cancer now? I'm going to show you, first off, one of the most popular methods. It's called the tree diagram. To do the tree diagram, you need to notice the wording here. If you have breast cancer, this probability depends on, it's conditional. It's backwards on the camera. It's conditional wherever that word is on the board. This is conditional on having breast cancer. Here, 97%, conditional on having breast cancer. This guy, though, is just straight the probability of having breast cancer. So when you make the tree diagram, look first for the percentage that is not based or conditioned on anything else. And that is the one that we're going to use for our first branch. So the first branch is going to be, do you have cancer or not? Now the probability of cancer is 0.0147. Please notice that I took this percentage and changed it in decimal form by sliding that decimal over 2 places. There's lots and lots of times that a student will put 1.47 here, and then they get ridiculous answers, and they get red X's because it's wrong, and they get so angry. No, first change it into 0.0147. How did I get this number? Well, if 1% have cancer, how many don't have cancer? It's just 1 minus this. 1 minus 0.0147 is 0.9853. You can check that you're doing the tree diagram correctly if the numbers up and down add to 1. For the next branch, what we're going to have is this. Did your test say positive or not? So now each one of these branches is going to have a test positive and test negative like this. Now, can I put those numbers into my tree? What do I have? If you have breast cancer, that's this branch. Then the probability of the screening finding it, which is a positive result on the test, right? Tested positive for cancer, that is 92%. So 0.92 goes there. Where does the other number go? 0.977. That's if you do not have breast cancer, down this branch. If you do not, then the screening shows that you do not. That means you tested negative for cancer. That's this one down here, 0.977. Don't fall into the trap that just because you thought it was the top branch here, that means it's going to be the top branch there. You've got to think to yourself, where does this number belong by following the scenario? Now that I know it's 92%, how can I get this guy? Well, it's just going to be the opposite. It's going to be 0.008, the decimal. And now that I know 0.977, what goes here? I'm going to have 323. What I'm doing is I'm taking 1 minus this to get the other one. Now my tree is all filled out with the probabilities for each of these 4 scenarios. This scenario is a woman who has cancer, and the test shows her that she has cancer. Is that good? The answer is yes, it's good. We want her to know she has cancer. Here, a woman has cancer, and the test says she does not. This is bad. This is someone who's going undiagnosed and could be getting help. No cancer, and the test is positive. This is also bad. Someone who is scared. Here we have no cancer and the test is negative. This is good. They're okay and they need to know that. All right. Now for each of these scenarios, we can ask the question, how likely is it? How likely is it that a random woman will have cancer and the test is positive? We multiply these two probabilities together. So when you take the two probabilities, multiply them together, and we get 1% of the time. Very rare, and that's because there's not that many women with cancer. Now, how often does a woman with cancer show no cancer on the test? Less than 1%. Good, we worry about that because that's a bad thing. What about a woman who has no cancer and the test shows positive? That's a bad thing. It only happens about 2%, which isn't all that often. That's good, that helps us to feel better inside. No cancer and the test is negative, that's about a 96% chance. So let's revisit this question. If the test does detect cancer, okay, so which of these scenarios do we not need? Well, here it detected cancer. Here it detected cancer even though it wasn't real. This is where it didn't detect cancer, didn't detect cancer. So those two scenarios are the scenarios that we want to burn. Notice the red marker flames is supposed to look like flickering flames. These scenarios are not parts of our story. We know that it did detect cancer. So, which story is it we want the probability of? This one. This is what we want the probability of. It's going to go on top. But it's not 100% anymore. These used to add up to 100% and they don't. Remember, when you're given information, you want to divide by not the original total. You want to divide by something else. What are we going to divide by? The new total. These scenarios put together. What do they add up with? Well, I'm running out of room, so let me destroy some of my tree diagram and put it on there. So here's the probability that we want. Having cancer where the test was positive goes on top. Here's our new denominator. These two pieces together add up to that new denominator. If we divide these, that will tell us the probability that you actually have cancer if the test is positive. Are you ready? This is going to shock you. Okay, believe it or not, if the test shows positive, there's less than 50% chance that you actually have cancer. That's why a doctor never says the test shows cancer. The doctor always says the test suggests you come back in for more testing. I personally have relatives where their test showed positive, the doctor had them come back in, and it turned out they did not have cancer. So why do we do cancer? This is actually a debated topic. If this is such a low probability, and the answer is I've had relatives who have had cancer, and it's a very serious disease. So we're willing to go through with this, even though this is a big thing. Now, if you had trouble following what I just did here, that's okay. Watch some of the other videos, other methods, and other examples to help you get it.